This is one of the schools that participated in the solar harvest scheme. Many solar panels have been installed here. How is their performance? Let's take a look.
EMSD introduced the Solar Harvest Scheme in 2019 to promote the development of local renewable energy. The solar energy generation system is equipped with a real-time monitoring system which records real-time data. For example, the solar irradiance, daily and monthly yield, total yield, and the amount of carbon reduction. The data can also be downloaded for educational purposes.
Dr. Tong, I wonder how the RTMS data are analysed.
I have the data downloaded. You can look at these two graphs. The first one shows the solar irradiance. The unit is watts per metre squared. The second one shows the output power of the solar panels. The unit is kilowatts. You can see the change within a day as shown in this computer simulation. The sun rises in the east. Sunlight shines obliquely when the sun rises. When the sun reaches the highest position in the sky, sunlight is directly incident on the solar panel. Recalling Lambert's cosine law, when sunlight is incident normally, solar irradiance is higher. Therefore, the graph shows a relatively high irradiance at noon. The output power of solar panels is also higher. In contrast, in the early morning or at sunset, sunlight shines obliquely. Both the solar irradiance and output power are lower. As shown in the RTMS data, the output power is in discrete levels but not continuous. This is because the values are 15-minute averages.
The incident angles of sunlight are different in summer and winter. Does it affect the output power of solar panels?
You are smart. I just meant to explain it. Let's look at the computer simulation. The Earth revolves around the Sun, as everyone knows, but the Earth's rotation axis is not perpendicular to the orbital plane. It is tilted by 23.5 degrees. We can see that near the 21st of June, the Earth is in this position. We take Hong Kong as an example. It is in the Northern Hemisphere. The Northern Hemisphere is more exposed to the Sun. Sunlight falls directly on the Tropic of Cancer. This is the summer solstice. Hong Kong is near the Tropic of Cancer. At that time, the sunlight is directly incident on Hong Kong. The sun is right above our heads at noon. When the Earth moves to the other side, which is near the 22nd of December, the Earth is in this position. The Southern Hemisphere is more exposed to the sun. Sunlight falls directly on the Tropic of Capricorn. This is the winter solstice. Sunlight shines obliquely on the Northern Hemisphere. In Hong Kong, you will find the sun to be lower in the sky. Solar irradiance is also lower. Near the 21st of March and the 23rd of September, sunlight falls directly on the equator. These are the vernal and autumnal equinoxes respectively. On these 2 days, the solar irradiance is in between that of summer and winter.
I know that seasonal changes affect the incident angle of sunlight. If we look at the sun from the Earth, will there be any difference?
The computer simulation shows the motion of the sun in the sky within a day in different seasons. The large hemisphere represents the sky we see. The green plane is the horizon. In summer, the sun does not rise exactly in the east, but in the northeast. It reaches the highest position in the sky at noon and sets in the northwest. In winter, the sun rises in the southeast. It reaches the highest position in the sky at noon and sets in the southwest. In summer, the sun is higher in the sky. At noon, sunlight is incident normally onto the ground. Do you still remember Lambert's cosine law? When sunlight is incident normally, solar irradiance is higher. With a better configuration, solar panels can receive sunlight more effectively. The power output will be higher. In winter, sunlight shines obliquely. According to Lambert's cosine law, solar irradiance is lower. The output power will also be lower.
I have noticed that in summer, the sun is above the horizon for a longer duration. More electricity can be generated.
Yes, in summer the sun is above the horizon for a longer duration. In winter, the sun is above the horizon for a shorter duration. This is the variation of sunshine duration. It also affects the electricity generation by solar panels. The sunshine duration and the angle of sunlight are the two factors that make summer hot and winter cold. The performance of solar panels is also better in summer than in winter.
From the RTMS data, can we see the effect of seasonal changes on the electricity generation by solar panels?
I've downloaded the data for 2 days. One day is near the summer solstice, the other day is near the winter solstice. For a fair test, the 2 days chosen have similar amounts of clouds. The data of cloud amount is obtained from the Hong Kong Observatory. Both were about 60%. This graph shows how the solar irradiance changes within a day on these 2 days. This graph shows the output power of the solar panels on these 2 days. Do you see the difference between the curves?
Both the irradiance and the output power fluctuate within a day, but in general the electricity generated in summer is more than that in winter.
You're right. In general, both the solar irradiance and the output power are higher in summer. This verifies the effect of solar irradiance as mentioned. In summer, the sun is higher in the sky. The solar irradiance is higher. Why are there fluctuations? We have mentioned that the cloud amounts were quite high on those days, which were about 60%. When a cloud passed through and blocked the sunlight, both the solar irradiance and the output power suddenly decreased. The values bounced back when the cloud left. This gives rise to the fluctuations. Take a closer look. The sun rises earlier in summer. The data is thus observed earlier.
Yes.
For sunset, the sun sets later in the evening. The sunshine duration is longer in summer and shorter in winter.
Now I understand that, but the weather in Hong Kong varies a lot. We need to pay attention to the weather so that solar panels can operate more effectively.
That's right.
The visible light in sunlight consists of light of different colours. They have different wavelengths. How do we know which colour is more abundant and which one is less?
To study the sunlight reaching the ground, like which color is more abundant and which one is less, there is a way. We use this portable spectrometer.
What is a spectrometer?
We have learned that a rainbow is formed when sunlight passes through a prism. That is a spectrum. If we want to measure the intensity of different colors or different wavelengths of light, we'll need a spectrometer. After collecting the data, it can be presented in a graph. The intensity of light is on the y-axis. The wavelength is on the x-axis, which represents different colors. We can see the intensity of each color of light.
Let's launch the app.
Sunlight is collected by the optical fiber and transmitted to the spectrometer. As sunlight is very intense, I've prepared a small tape to be placed at the open end of the optical fiber. The small hole on the tape allows a limited entrance of sunlight. This prevents the apparatus from being saturated.
The app is ready.
Let me point the optical fiber towards the sun.
Let's check out the measurement. I see the peak around the green region. The intensities of blue light and red light are lower.
This shows the intensities of different colors. Why is there more green light? There is a reason behind it. The sun is a very hot object. All wavelengths of light, or light of all colors, are emitted by the sun. The surface temperature of the sun is about 5,800 Kelvin. Assuming that the sun is a perfect body emitting radiations, the peak of the spectrum is determined by its temperature. The peak is at about 500 nanometers, which corresponds to the yellow-green region.
If the optical fiber points towards the sky instead of the sun, what will happen?
Let me remove the tape to allow more light to enter. Now, I point it towards the sky.
Green light is more abundant when it points towards the sun, but why is there more blue light when it points towards the sky?
This is because of the Earth's atmosphere. The Earth's atmosphere is very important. It blocks a lot of radiations that are harmful to human beings. The radiations include ultraviolet and even X-ray. The harmful radiations are blocked by the atmosphere. They cannot reach the ground. The molecules in the atmosphere are capable of scattering sunlight. The scattering of blue light is more extensive than the light of the other colors. On a sunny day, the molecules in the atmosphere scatter the sunlight, especially the blue light. That is why the sky appears blue. When we look at the spectrum, blue light is more abundant. The peak lies in the blue region.
The atmosphere is so helpful. Besides visible light, are there any other electromagnetic waves that can reach the ground?
Sunlight consists of many different kinds of EM waves. Let's look at this graph. It shows the spectra of sunlight. The yellow curve is obtained in space. It is not affected by the atmosphere. The red curve is obtained on the ground after the absorption by the atmosphere. Do you notice that the red curve is lower? Other than visible light, sunlight also contains ultraviolet radiation. Most of it is UVA along with a little UVB. Some infrared radiation can also reach the ground. In previous experiments, we found that not only visible light is useful for solar energy generation, but also infrared radiation. Ultraviolet radiation is useful too, but with lower effectiveness.
When compared with the curve obtained in space, why are there some missing parts in the curve obtained on the ground?
The water and carbon dioxide molecules in the atmosphere are exceptionally effective in absorbing infrared radiation. Most of the absorption lies in this region. It is the consequence of the absorption of water and carbon dioxide. There is some absorption in the visible region, but it is not as significant as that in the infrared region.
The atmosphere has such an influence on sunlight.
So we need to protect it. If more ultraviolet radiation reaches the ground, we'll be harmed.
Or tanned. Now I've learnt about the solar spectrum, but I still don't know how the weather affects the electricity generation by solar panels. On sunny days, more electricity is generated. But on cloudy days, electricity can't be generated. Am I right?
You're almost right, but electricity can still be generated on cloudy days. Let's look at the RTMS data. We compare 2 days. One is a sunny day with a low cloud amount, the other is a cloudy day. To fairly compare the effect of cloud amount, the 2 days are chosen close to each other. This minimizes the effects of the seasons. We can compare the difference due to the cloud amount. Can you see the difference between the two curves?
The curve of the sunny day is very smooth. The overall output power is also much higher. On the cloudy day, the output power is much lower. The curve is not as smooth as that on the sunny day. It fluctuates a lot. Why is that?
Here are 2 graphs. One shows the solar irradiance. The other shows the output power of the solar panels. As you just said, the curve of the sunny day is higher and smoother. The curve of the cloudy day is more irregular and much lower. The reason is that there were no clouds on the sunny day. Sunlight constantly reached the solar panels. The output power of the solar panels changed only because the incident angle of sunlight varied. The change in the angle of incidence was slow, thus the curve is smooth. The solar irradiance is maximum at noon. The output power is also maximum. It is apparent in the curve of the sunny day. However, on the cloudy day, the clouds blocked sunlight. Therefore, the solar irradiance and output power were both lower. When a cloud passed by, sunlight was blocked. The solar irradiance and output power suddenly decreased. The values increased again when the cloud left. As a result, the curves fluctuate.
Now I know the effect of weather on the electricity generation by solar panels, but I'm still confused. On cloudy days, clouds cover the sky. The sunlight can't reach the ground. How do solar panels generate electricity?
You are right. But what you are talking about is the direct sunlight falling on the solar panels. Apart from direct sunlight, there is also indirect sunlight.
Indirect sunlight?
Sunlight can be scattered and reflected by clouds. Some light can somehow reach the ground. Moreover, solar panels can absorb other radiations, such as infrared radiation from the surroundings or infrared radiation from the sky and the clouds. Solar panels can absorb them. On cloudy days, solar panels can still generate electricity with these radiations. But the power is indeed not as high as with direct sunlight. Therefore, the output power of solar panels is much lower on cloudy days.
What is the effect of weather throughout the year?
I have downloaded the data for analysis. The graph shows the monthly average of output power of the solar panels within a year. The bar chart shows the output power. The broken line shows the monthly average of the cloud amount. When the cloud amount is higher, the output power is lower. The output power is higher when the cloud amount is lower. They have an inverse relationship. This shows that the output power of solar panels is significantly affected by weather. The effect of seasonal change is insignificant when looking at the monthly average values.
I see. Solar panels generate power every day and every season regardless of the weather. Just like me, right?
Yes, that's right.
Now we know how seasons and weather affect the output power of solar panels. The variation seems to be complicated, doesn't it?
The output power of solar panels is affected by seasons and weather. However, these factors are out of our control. But we can take some adaptive measures to increase the efficiency of solar panels. You've been to the school under the Solar Harvest Scheme and visited the solar panels. Did you notice anything special about their configuration?
They're all inclined. I don't get it. Shouldn't they be laid flat on the ground? It seems that more sunlight can be absorbed if they face the sky.
I'm going to explain this. Let's look at the computer simulation again. It shows the sun paths within a day on summer solstice, winter solstice, vernal and autumnal equinoxes. The sun is seldom right above our heads. During summer in Hong Kong, the sun is almost right above our heads at noon. But in spring and autumn, or winter, the sun lies in the south at noon. Sunlight comes from the south at an angle. If the solar panels face upward to the sky, the efficiency is lower. The sunlight shines obliquely.
The solar panels should be tilted. Dr. Tong, how about the angle of inclination?
How much should they be tilted? There are many factors to consider. The first factor is the latitude. Hong Kong is at 22.5 degrees north. We skip the extreme cases such as in summer and winter. Let's consider the cases in spring and autumn. If we want the solar panels to face toward the sun at noon, they should be tilted by 22.5 degrees, which is equal to the latitude of Hong Kong.
But it seemed that the solar panels in the school were not inclined by up to 22.5 degrees.
The angle of inclination is not that large in practice. There are many other factors to consider. The sunshine duration is longer in summer. The sunlight is more intense. We want to get more sunlight in summer. The solar panels are thus inclined at a smaller angle so that they can absorb more sunlight in summer. There are engineering considerations too. If the solar panels are inclined at a large angle, more materials are required for counterweight. They will become heavier. With a larger angle of inclination, the stability is lower. Hong Kong is windy, especially during typhoons. Strong winds may blow away the solar panels. Also, if they're inclined too much, large shadows may form behind them. They may block the sunlight that should have fallen on the adjacent panels. Then they have to be placed farther apart. This would be a waste of space, given the space on the rooftops is limited. Taking all the factors into account, the solar panels are inclined at a smaller angle.
There are many factors to consider. The installation of solar panels is not as straightforward as it seems. What's the angle of inclination in the schools of the Solar Harvest Scheme?
After a careful assessment by engineers, the solar panels are inclined by 14 degrees. Different factors are balanced. After experiments, it was found that the difference between 14 degrees and 22.5 degrees of inclination has an insignificant effect on the efficiency of solar panels in Hong Kong. However, it is safer to incline them at 14 degrees without compromising efficiency.
Apart from the solar panels on the rooftops, are there any other facilities for solar energy generation?
With the help of modern technology, the efficiency of solar panels can be increased. For example, in the headquarters of EMSD, there is a concentrated solar panel. It can converge sunlight as well as following the position of the sun by adjusting its orientation. It can track the sun. Moreover, the Water Supplies Department and Drainage Services Department have installed some floating solar panels in the reservoirs. This helps save on land use.
That's a smart use of space. I like it.
It is vital to use the resources of Mother Earth wisely. The reports published by the Intergovernmental Panel on Climate Change state that human activities cause global warming and has led to more frequent and severe extreme weather conditions all over the world. Global warming results in the rise of sea levels. In the long run, it poses a threat to low-lying areas. The interrupted climate also brings about more frequent extreme weather events. For instance, super typhoons and heavy rainfall, etc. In 2017 and 2018, Hong Kong was severely hit by super typhoons Hato and Mangkhut, respectively. They caused severe devastation. If we're reluctant to make any changes, the threat of climate change to us will be larger. To cope with climate change, we should take prompt actions to reduce carbon emissions and achieve carbon neutrality.
In 2021, the Hong Kong SAR government announced Hong Kong's Climate Action Plan 2050. A series of strategies and targets were set with a view to achieving carbon neutrality before 2050.
The Paris Agreement was signed in 2016, which set targets to combat climate change. Carbon neutrality is achieved by replacing fossil fuels, energy saving, and afforestation. These actions help reduce or offset carbon emission and limit the increase in carbon concentration and global temperature. It in turn reduces the risks and damage caused by climate change.
The government has been taking the lead in developing renewable energy, including raising the requirements of applying renewable energy technologies in government buildings and developing renewable energy projects of different scales and suitable premises. Solar energy is one of the renewable energy suitable for development in Hong Kong.
Everyone has put in a lot of effort. We need to keep working together
to achieve
carbon neutrality before 2050.